We're looking onto the Coolins on the Isle of Skye in Western Scotland. This area, and others like it in Western Scotland, are the birthplace for many of the ideas we use to interpret the deep structure of volcanoes, so-called subvolcanic complexes. And this understanding comes from mapping that was carried out in the early part of the 20th century. What we're going to look at here are some of the map patterns that came from that mapping and use them to infer the 3D geometry of a number of features. We're going to look at lavas and we're going to look at the intrusions of various types. And we're going to look at the geometry and map patterns for these units, how they interact with one another, and how we can use these relationships to build a geological history. And we can use the maps that came out of that research in the early part of the 20th century. So where are we talking about? Well, this is a map of northwest Scotland, and the igneous centres we're concerned with are shown in black on here. These units were developed in the early tertiary and are associated with significant lava fields shown on the map in green, and they continue in the offshore under the Sea of Hebrides and the Minches. So the black areas are the subvolcanic complexes. There are lava fields, but there are also minor intrusions that are too small to be shown on a map like this, but we'll look at them in more detail as we go. So here's an example of some of the mapping that we'll use. We can use two types of maps at different scales. The more generalised map is developed at 1 to 253,440, so-called quarter-inch map, where a quarter of an inch represents 1 mile. We'll also use the more detailed maps, the 1 inch to 1 mile series, at 1 to 63,360. Modern map series that use these types of scales would be for the more detailed at 1 to 50,000 and a more regional scale at 1 to 250,000. But we'll use the original, which were developed on an imperial length scale. So the geological map on the right there, which includes the Isle of Mull, is shown on the regional map on the left in that boxed area, and the more detailed map in the middle there of the island of Egg is shown in the boxed area on the right-hand map. So let's begin our tour on the Isle of Mull. The main subvolcanic complex is shown by that area where there are concentric ring-type structures, and we'll just loop those for now to identify the main centre there by the red blob. So that is the roots of the old volcano that was there. Surrounding it are flood basalts shown in the pink. These are lava fields, and as I said at the start, they continue offshore in the subsurface, but this is just showing the onshore geology. And then crossing the lava fields, and indeed parts of the main centre, are a set of streaks on the map here, which is a dike swarm running from northwest to southeast, approximately. So let's go and look at some of this geology, and we'll zoom onto this area on the Isle of Mull. So this is part of the map sheet published in 1923, and it's part of this 1 inch series. Let's zoom in, and what we can see on the map around Inchkenneth, that island, it are those orange rocks which are Triassic, so these are sedimentary. The Triassic rocks are overlain by a thin veneer of Jurassic that underlies the lava fields. And the lavas are shown on the right-hand side of that blow up in the pink. And the boundary could be traced like this. So this is the base of the lavas. The lavas obviously erupted across the sedimentary rocks. So what about the structure of the lavas themselves? How have these been displayed on the map? Well, to answer that, we're going to just skip away. So this is the area we're looking at, and now we'll go over to the island of Ulva, just to the northwest of the area we were looking at. And let's see how the survey mappers picked out the internal structure of the lava field. So here's the island of Ulva, and you can see that the island is almost exclusively made up of these pink rocks on here, which are the basaltic lava flows. Now, within that pink outcrop, you can see those thin black lines that wiggle through the landscape. I'll just pick some of them out. These track the layering within the lavas. In other words, they represent the flows. So what the geologists have done is trace these out within the single unit of the lavas. It's called form surface mapping. So if we zoom in on that area there, the point of that exercise is to show the trend of the layering within the landscape, and it demonstrates that lavas are layered subhorizontally because the shape of these wiggly form surface lines more or less follow the topographic contours. So those are the techniques used to show the structure of the lava fields. What about the dike swarm? We can see that they cut the lava field. Well, let's just skip away from Mull and go to another part of the Inner Hebrides, the island of Muck. And you can see on this map, which was produced or published in 1908, it shows mapping by pioneer Igneous geologist Alfred Harker, and the map is hand-coloured. The pink and green are the lavas, and cutting across the map are those diagonal stripes of thin strips of red, which are the basaltic dikes. And because they run from sea over the island and down to sea level again, as you imagine walking along one of these dikes, they roller coaster across the landscape in outcrop pattern without deflecting in trend. So the dikes must be vertical. And they trend on that bearing of about 330. So we can use the map pattern to determine the orientation of the dikes. Let's turn our attention now to the main Igneous centre. And here's part of the 1-inch map series published in 1923. It's a very famous map, and the mapping was largely completed by E.B. Bailey. Let's zoom in. Fantastic detail. So it shows various compositions of intrusions cross-cutting one another. And the pattern is rather curious, isn't it? It's not like the dike swarm, which were forming straight patterns. The shape of the outcrop traces of the different units in here are forming sort of concentric arcs. So Bailey showed the structure of these in some cross sections. Here we go, they're coming through that part of the map shown by the white stripe, and these were sections put together for an International Geological Congress field excursion in 1948 that visited Mull and Ardnamurchan. So these intrusions are inclined and they make arcuate patterns at outcrop. These arcuate patterns are typical of many of the volcanic centres in this part of Scotland. So let's skip away from Mull and look at a really classic example over in Ardnamurchan. It's a great place to visit. Here's the geological map, a part of the 1-inch series for Ardnamurchan, just the very end of Ardnamurchan Peninsula here. And again, you can see the arcuate shape of the various colour strips, which are different compositions of igneous rocks within this subvolcanic complex. It's a ring complex. So the intrusions make arcuate patterns at outcrop, and they are inclined towards the centre of their ring shape. In this sort of shape, in other words, they're conical intrusions. So these subvolcanic complexes are made up of conical intrusions that are nested together. They developed really complicated cross-cutting relationships. They didn't all come in one go, of course. They came in a series that cross-cut one another. And you can see some of these cross-cutting relationships on the map. So let's turn our attention now to Skye, which is the largest of these centres. And it's a composite system. So here's a map published in 1909 for this corner of Skye. Let's go on our tour. So let's start off down here and we'll look at another type of intrusion geometry. Here's a blow-up of this from a more recent map published in 1963. It shows the same geology as the original map, but is now on a kilometre grid system. So what we have here is a granite in red that intrudes limestones in blue around the margins. The edges of the limestones with the granites are now marbles because of the contact metamorphism. This is the Benanduit granite. So what's the geometry of the margins of this granite? It's clearly quite complicated because of these strange patches of limestone that are floating around within the granite itself. It's a complex boundary. Well, to understand this, let's just sketch up a cross-section that goes sort of northwest-southeast across some of these floating pieces of limestone. Here we go. So here's a cross-section just cartooned up. And we can see that in this interpretation, the patches of limestone within the granite are interpreted as dangling down from above. So originally, the roof of the granite was highly irregular. These types of features are generally referred to as roof pendants, so dangling bits of roof of the intrusion caught up in the outcrop pattern. A highly irregular intrusive boundary, quite distinct from the ring complexes we looked at before and the dike swarm. So much for the various intrusion shapes that we can pick out. Let's think about the relative timing of the different intrusions. And let's go here into this part of the map. The pink on the map, and the green indeed, are lava fields. And we're looking at a little strip along the side of those pink rocks which are granite, and the final part of this are various types of basic intrusion. So let's look at the photograph and make sense of what we're looking at in here. Here is a lava, there's the granite, and there is a basic sheet. So what are the relative ages of these three units? Well, the granite intrudes the lava. So therefore the granite is younger than the lava. But what about the basic sheet? Well, the basic sheet cross-cuts both, so is the youngest of all. So therefore, in this outcrop, we can deduce a timing simply from these intrusive relationships. What about the dike swarm as a whole? Well, we can see the dikes running across the map on here, running northwest-southeast. And we've seen when we looked at the island of Muck that the dike swarm is essentially a vertical feature. We can also maybe deduce this from the map pattern here because they're trending right up and across various mountainsides here without changing trend on the map. Well, an interesting feature here is that different units have got different numbers of dikes or different densities of dikes within them. The lava fields have got quite a lot. The granites, the red rocks on here, certainly at the margins of the map, at the top left and top right hand corners, have got very few dikes indeed. There's another igneous unit in here, which are gabbros, which are the grey rocks that are running from the top down to the left hand side of the map. Well, let's do a count. Let's count the number of dikes encountered on two transects of equal length, one in the lava fields, one within the gabbro. There are 13 dikes in the gabbro and 17 in the lavas. Now, from the map pattern, what about the age of the gabbro relative to the lavas? Well, the gabbro intrudes the lavas. It's an intrusive unit. So here's the intrusive contact between the gabbros and the lavas. So the gabbro is younger than the lava fields around the edge. What's that mean about the dikes? So let's imagine this dike swarm being built up gradually. So you have one dike, then another dike, and another dike. And that history has continued throughout the igneous history of the region. So the other igneous rocks will contain different numbers of dikes depending on how young they are in the story. The lava field is relatively old, so it's had more dikes intrude it. The gabbro here is rather younger, so has had fewer dikes intrude it because some of the dike swarm were already intruded before the gabbro itself was in place. What about the granites? Let's go back to Benenduik where we looked at those roof pendants. Here's that map again. Where are the dikes in the granite? There are none in the granite, but there are dikes in the wall rocks. So clearly this granite was in place after the regional dike swarm was largely finished. So this implies that the Benenduik granite and its associates are rather late in the igneous story. So we've inferred that the dike swarm was intruded throughout the history, that older units therefore have more dikes than younger ones. It implies that the granites, the red rocks on these maps, are a relatively young part of the sky igneous centre. There are lots of dikes in the lavas because they were there first. There are fewer in the gabbros because they were there emplaced and intruded after the lava field, and very few in the granites because those are the youngest still. Well, let's see how this bears out when we look at the age relationship between the granite and the gabbros. And we're going to go here. Here's the view. The mountain at the back is a hill called Blaven, and the landscape betrays the geology really well. Those rugged black rocks at the back going up to the high point over there, the mountain Blaven, are gabbros. The rounded hill, and indeed the foreground, which makes much paler rock outcrops, are granite. And we inferred from the map pattern just now that the granite should be younger than the gabbro. So let's go and have a look at the contact. So here's the map for this ground, published in 1904. And we're interested in just the very small part of it. Here. The granite on the right-hand side of the map is in pink. The gabbros are grey, and various minor intrusions are shown by those little green strips and the red strips, largely concentrated, or wholly concentrated, within the gabbro. Now, this issue about the relative age of granite and gabbro in this location was a point of major controversy in the last few years of the 19th century, and it led to really heated debates. Here's the ground. Again, the granite is really obvious in the landscape in that red, and the gabbro forms the foreground. And remember, the granite should be younger than the gabbro, so let's look at the contact itself. There we go, and the granite clearly intrudes the gabbro along those little fingery intrusions. So the granite is indeed younger than the gabbro. So basic field observations tied to the geological map resolve that debate. Map patterns on the sky allow geologists to infer the relative age of the granites and the gabbros and to build a geological story, a story of the relative ages of intrusion. We've used the outcrop patterns collected and reported on these old geological maps to infer 3D geometry. Different igneous rocks have got different types of boundaries, from the simple ones of the lavas and their internal structure, to the very steep dike swarms, to the increasingly complicated intrusions of the conical sheets, and then these granites. So different igneous rocks have got different types of boundary. They interact with one another, and we can use these relationships to deduce a geological history. These approaches were developed in the early part of the 20th century, and they remain relevant today.